Yep, did not post it, will not post it until later. Have fun doing test corrections.
Oh, yeah.
Yeah, you don't always get to do those in Calc 3. All right. Chapter 14. This is the end. Question, Rachel?
Can we use our notes when we're doing test corrections?
Yes, you can use your notes. You can use your note. You can use anything but a friend. No phone a friend. No phone a friend. I guess you can phone Siri. She's helpful. She's actually very helpful.
Really? We phone an enemy.
Well, her and phone a non-friend.
So
Siri talks to Wolfram Alpha. That's how she gets all her math done.
so all you have to do is make sure Siri can actually understand what you're saying.
Yes. Yeah. That's the hard part. Okay, so let's go to chapter 14. Chapter 14. Vector fields. You've already done one vector field without even knowing it. And that's the gradient vector field. So a vector field, let's start that. A vector field is nothing more than a collection of vectors on some domain. And we already know how to find the gradient vector at a point, and if you imagine all the gradient vectors on a surface or in a region in the plane, however you want to imagine your domain, that's a vector field. A vector field is just a pincushion of vectors. You know, they're defined at either at an ordered pair or at an ordered triple. Usually we will represent our vector, that's wide. We'll usually represent our vector fields that way. The IJ notation gets really messy, but you're more than welcome to use it if you want.
I think it seems to be used a lot in physics.
Yeah, physics folks love to use the IJ notation.
Except that I generally do the angle notation.
Yeah, I think it's so much easier. It's very easy to drop, you know, if one of your components is 0, all of a sudden you're in 2 dimensions instead of 3. When you have the angle brackets, you always know what the ambient space is. I prefer the angle brackets. Okay, so let's take a look at some examples. Here is a vector field that is radiating. This vector field, we're going to learn a couple of words. We're going to learn a word called divergence, and we're going to learn a word called circulation. This vector field has lots of divergence, but no circulation. And the idea here is that whatever the initial point of the vector is, you plug that into your vector field formula, and that tells you how to create your vector. So you go to x comma y, take those coordinates, and the vector defined at that point is found by plugging the coordinates into the vector field equation. So here's our vector field equation, 2x comma 2y. So if we went out to say the point, I don't know, say 4 comma 1, the vector would be 8 comma 2. So that is how you determine what a vector is, what the vector is that corresponds to a point. You just plug in the ordered pair and you're good to go. Here's another vector field. So again, you're just going to plug in your ordered pairs. So if we were at the point, I can't even see that, I guess that's not a number. Oh no, that is a 1. So if we're at the point 1 comma 0, we would plug a 1 in for x and a 0 in for y. Since there's no x's up here, we're just plugging in a 0 for y, and the vector that emanates from 1 comma 0 will be 1 comma 0. That vector field has some circulation and some divergence. So we'll talk about why as we analyze vector fields more carefully. The ones with no circulation and lots of divergence, or lots of circulation and no divergence, are totally obvious. If it's not obviously one or the other, it's going to be some balance between both circulation and divergence. We'll see. Like this one, lots of circulation but no divergence. This one is going to be a mix. There's going to be some circulation and some divergence. So that's how we find how we find representative vectors. We can't plot all the vectors, or you'd see nothing. Right? It would just be all red. Right? If you put every single vector from the vector field on there, it would be a mess.
Maybe you could just do color blocks with arrows scribbled on them in a contrasting color.
Color on color. So you
Yeah, just like
feel
red,
a
red block,
painting.
and then to point in the direction you just draw blue arrows all over.
The rule of thumb is to just draw a few vectors so you get a sense of what's happening. Not too much. Don't draw too many. Just a few. Just a few. Here's one type of vector field that you see a lot, especially in physics. You see these radial vector fields, things that are going in a straight line essentially from some central location. So here the vector field is the ordered pair written as a vector divided by the length of the vector raised to some power. So you'll see lots of those types of vector fields when you're dealing with electricity and magnetism and gravity, depending on the scale. Lots of these radial vector fields. The magnitude of this vector field here is going to be that, 1 divided by the length of r to the p minus 1, because we're going to use, you take the length of this vector field down below, that's a scalar. So up here, the length of r is whatever it is, and then we would have to cross one of those factors of magnitude r out, so we get a magnitude of 1 divided by length r to the p minus 1.
So what does R represent again?
R is representing the vector. R is representing a position vector.
Okay.
So R is a function, comma, another function. Possibly a function, comma, another function, comma, another function if you're in 3 space. So R is a vector.
Wait, question.
Question, yeah?
So, if you can replace r with that x comma y, couldn't you also replace it on the bottom? So it's just a normalized unit vector that points in the direction of them?
You could absolutely, yeah, you could have R being any number of things, and then the length of R in the denominator. Like, that's not a unit vector in this case. If R is a unit vector, then the denominator is 1.
But if you have xy on top, and you
Mhm.
divide by some power of xy,
Mm-hmm.
the length of it essentially, then you get a...
Oh, I see what you're saying. But the magnitude, if you do the magnitude raised to a power, that's a little different than just dividing by the magnitude. Certainly, if you take R and divide it by its length, that is a unit vector. Yes, yes. But if you raise it to a power, then is it no longer a unit vector?
Gotcha.
Yeah.
So what determines the power, or is that one thing we're going to figure out?
That's just, it's random. You might have a radial field where the power is 2, you may have it where it's 4. That's just sort of random. They're just saying in general, if you've got these vectors that are emanating from some central point, regardless of what the scaling factor is, we're going to call it a radial vector. So if you take your position vector x comma y, and then you scale that vector, make it longer or shorter in that direction, they'll call that a radial field. So you imagine light, going out, or something like that. So vector fields can be in 2 space or 3 space. If they're in 3 space, we have an FGH, 3 components instead of 2. Nothing that complicated. Just put an extra position. And then same idea down here. You could have a radial vector field where we're in 3-dimensional space. So a radial vector field would be xyz divided by some number. Regardless of what p is, you still have a scalar in the denominator. P is a real number. So if you take an ordered pair or an ordered triple and you turn it into a vector, then you're just emanating from the origin as a vector. Grant?
When you're handwriting the equation of a vector field, since you can't very easily bold something when you're handwriting, is it the same as the vectors where you just put an arrow over it?
Yeah, that's right. We would just do the exact same thing that we would do with a single vector. So the big difference is now we have components, so now we're thinking of it as a function now, right? Which we kind of did a little bit before, but there wasn't an emphasis that it's a function. Like, this is a function on the entire real plane. And so now we think a vector field is just a function. It's just a function that gives you a vector for every ordered pair in the domain, or ordered triple. So let's try a couple. So this vector field, let's just get a sense of what it looks like up there. So pick a point. I don't know, 2, 3. So if we pick 2, 3, that's right there. Then we have to figure out what the vector is that's applied at that point, 2, 3. So we go up here and it says, okay, let's do this. Let's write it though so that we are clear. So that ordered pair is going to go to the vector -2, -3. So that vector gets written or drawn right at that point. So -2 in the x direction, -3. Oh, doesn't that just go right back to the origin? Everyone okay with that? Let's pick another point. Let's say we pick, let's pick something over here, -6, 4. So according to our vector rule up here, we're just going to switch the signs. So we're going to go 6, -4. So we'll go to -6, 4, which is right here. And then the vector that we apply says go 6 in the x direction, and then 4 in the y, down 4 in the y direction. So that's going to give us another vector right back to the origin. So this vector field, everything is converging on a single point. This type of vector field, this point 0, 0 will be called a sink. It's just everything is flowing towards that one centrally located point. So it's a sink.
Is that just because it's just x, y in the vector thing?
Yep. In the components of the vector field, we're just reversing the signs of the position of x, y, so that just forces everything to go to the origin. So I call it a sink, because everything's coming to one point. The other type of vector field, the radial vector field, a lot of times that's called a source, if everything's emanating from a single point. Let's come over to this one. Same idea. We're just going to pick a couple points. So let's pick 7, -2. There's 7, -2. We look at our vector field formula. It's going to generate a vector. It says take y and put it in the first position. Take the opposite of x, put it in the second position. So from there, we're going to go -2 in the x direction and then -7 in the y direction. So that's 3, 4, 5, 6, 7. I think we're going to be right there if I counted right. That would be our vector pointing down in that direction. The 0 vector, let's just make sure we do at least one with the 0 vector. 0 vector is just a point in this case. Well, the 0 vector is always just a point, but here the origin corresponds to the 0 vector. If we picked -2, let's pick one point just for grins. If we pick -2, 3, according to this vector rule, we're going to go 3, +2. So we go to -2, +3. Then we're going to go right 3 and up 2. So that will be our vector. A lot easier than graphing hyperbolic paraboloids. Okay, so nothing complicated yet. We're just sort of getting the sense that a vector field is really just a function of vectors. Every point in the plane, every point on a solid, we imagine all these little vectors pointing in whatever direction. Question, Grant?
It just doesn't look like that last point is very accurately graphed, at least the
On this side?
on the right side.
Oh.
That 3, 2 looks more like 1, 5.
So over 3, 1, 2, 3, up 2, 1, 2.
Oh, okay. I see what you're doing. It's
Yeah,
like
yeah,
the
yeah.
num-
So the
point.
ordered pair of the terminal point is different than the components of the vector.
Yeah.
So the components of the vector are always measuring from, it's a road map from the initial point to the terminal point.
Okay.
Yeah, good question. Make sure that's clear.
I have
Yeah.
So we would have to keep graphing to see like the because like there we can see the pattern pretty easily.
Right,
but
here the pattern, right. So for that, and there's a lot of graphing utilities that will graph vector fields.
Okay.
So, and I can't remember if Desmos does vector fields yet. There's a lot of graphing utilities where you can graph where it will show you, and we'll see some photos in here of vector fields that are generated by Wolfram Alpha or something. Yeah, because it is hard. How many do you graph? You know, before you get a sense of what's happening. There's no good answer.
Graphing, I'm starting to graph silver morning and still rather confused on what's going on here.
That looks scary.
Okay, so the gradient field, like I said, that's one we've seen before. So we're going to let phi be a differentiable function on R2 or R3, and the vector field that you create is called the gradient vector field. And phi is going to be called a potential function. So if we have a function and we take its gradient, we get a gradient vector field. Now, if you have a vector field, the question becomes, is there some function that has it as its gradient vector field? If I give you a function, you can always differentiate it. Right? Going backwards is the hard part. Right? So if I give you a vector field, the question might be, well, is there a function that has that vector field as a gradient field? So phi is acting like an antiderivative. If you find one antiderivative, there's going to be an infinite number. So phi plus k, they have the same gradient field. So not every vector field will have a potential function. Every function has a gradient field, though. I give you a function, you take the derivative, and you have a vector field. But you can imagine creating all sorts of weird vector fields that you can't integrate into one function. So that's going to be something that we'll analyze. So given a vector field, can we find a potential function? We'll have a very sort of antiderivative method to figure out if we can find a potential function for a given field. And like you already know, so the level curves of phi, those are the greens, and the gradient, right, has to be perpendicular to the level curves. The gradient is always orthogonal to level curves. So what big difference here is that we're imagining the gradient at an infinite number of points, which creates these curves. Right? And these curves are, a lot of times, are called flow curves. The flow curves are just orthogonal to all possible level curves. And sometimes they'll refer to the level curves as equipotential curves. Doesn't matter, call them level curves, equipotential curves. Depends on what the application is, whether you know, in math we just call them level curves. If you're dealing with electricity or magnetism or something else, you could call them something different. If you're dealing with temperature, they call them, what do they call them? What's the surface of constant temperature? Isotherm. Same idea. An isotherm is the surface that has constant temperature values.
Or topographical math.
Constant altitude. Mm-hmm. So let's take a look at this. We have a pretty simple vector field here, y comma negative x. And it says determine, and one clarification, quite frequently we're going to be looking at our vector fields applied onto a curve, or applied onto a region, or applied onto a surface. Or maybe throughout a solid object also. So that's going to be our primary, that's where we're going to go. We want these vectors from a vector field are going to be on some object, and then we have to sort of integrate them often. Okay, so it says determine points on this curve where the vector field is tangent to C. Let's just plug in some points, figure out a couple of data points here. If we look at this point right here, that point is 1, 0. What would be the associated vector? We're going to swap, and we're going to get 0, negative 1. So we're going to switch the y over to here, take the x and change the sign. So 0, negative 1. So that vector is just pointing straight down. Like that. That's definitely tangent. That's what it was asking for. Let's try another one. What about if we let's pick another quadrantal point first. Let's pick, say, this one. So that point right there is 0, negative 1. And where does that get mapped? What vector does that get mapped onto? So negative 1, 0. That also is tangential to the curve. Negative 1, 0. Looks like that. So definitely those quadrantal points look pretty good. Looks like we're going to be doing this kind of thing. It's like we're going to have clockwise circulation. Now, if we imagine a random vector that comes out from the origin that goes to our graph, isn't that vector right there x, y? So call that r, and r is equal to x, y. right? So on that circle, those are our points. The ordered pair is going to be represented by the vector that comes from the origin and has a terminal point at the ordered pair. What about if we take these two, let's take our R vector here and dot it with this. What happens if we dot those two vectors together?
You get 0.
Yeah, we get 0. So what that tells us is that all points on the circle have a tangent, well, have a vector from this vector field that's going to be orthogonal to it, which means all points on the circle satisfy what they ask us to do. Every vector from F is going to be tangential to the curve. Correct? Every vector. So like let's pick a point that we know. Let's pick a point like say -1/2. Let's call that P for a second. Let's suppose P is -1/2 comma, this is a unit circle, so √3/2. So that is a point on the circle. It corresponds to the displacement vector that comes from the origin and points right to it. So that would be the vector form of P. If we want to get sloppy, we can probably just do this and not make too many folks angry. All right, so there's P, and we know that it's going to be perpendicular to that vector. Well, if it's perpendicular, it's got to be tangent to the circle. So we know that its capital F representation is going to be orthogonal to it.
Wouldn't vector P be the y negative x 3?
Vector P is the vector that comes from the origin and touches the point. Now the vector that we build from F, the vector that corresponds to it from the vector field, we would do this and we would say, okay, that's going to be √3/2, comma 1/2. Oops, and I should put vector angle brackets. And that's this vector right there. Yeah? Like,
So is the interpretation of this the circles rotating the clockwise?
yeah, so this vector field, we have lots of circulation. Right? Yeah, so it's circulating around some central point. Circulation. Circulation. The toilet bowl vector field. Although, does the toilet bowls go clockwise or counterclockwise in the northern hemisphere?
I don't think that's true.
Yeah,
I don't think
depends on,
it's
like,
actually
the
dependent on
jet
that.
like, funnels
Oh,
out.
right, okay. So there's some mechanics involved?
Well, actually, it kind of reminds me of the graph of the velocities of a rotating object.
The what of velocity? What?
Yeah, so if you got an object that's going in a circle, then that reminds me of the graph of the instantaneous velocities.
Oh, right, yes, absolutely.
I want to see a vector field of the velocity of an African squirrel, but I want to see it across a map of Europe and Africa. And see
I
how
bet
it
it's on
changes.
the internet. Look it up on those
It's not, we have the power to put it there.
And African squirrels.
African squirrels. Okay, so let's take a look at one more of these things. Here's a potential function, phi, and they say find the gradient field. So we will do del phi, and all this is just the vector of partial derivatives. That's the gradient field. So phi sub x is 2y. Phi sub y is 2x. So that is the vector field. Phi is a surface, so you can think of it as z equals 2xy. But these are level curves for that surface. We're not graphing phi, but we're graphing a few level curves for phi. And if we pick some points that happen to fall on these level curves, we're going to create vectors that are orthogonal to those level curves by construction. We already have proved in a previous chapter that the gradient is orthogonal to the level curves. So pick a point. Pick a point on here. What's that? 2, 1 right there. So 2 comma 1, if we throw it into that vector, the vector is going to become 2 comma 4. And if we graph 2 comma 4, that is going to be a vector that is orthogonal to that level curve. So 2 comma 4, something like that. And it's not going to matter. You pick any point on one of those level curves, you plug the coordinates in, and you get a vector that's perpendicular. Let's see, let's pick another point. 1 comma 2 is right there. So 1 comma 2, where's our thing? 1 comma 2.
That's one.
Right there is 1 comma 2. So we're going to get 4 comma.
Wait, it's 1 comma 1 because the 2 line is all.
It's 1/2.
Oh yeah,
Um,
1/2 one.
This point, are we talking about this point?
Yeah.
Oh, sorry.
That's
What is it? 1/2 comma 1?
Yeah.
Sorry. 1/2 comma 1. Plug it in there, and we get 2 comma 1. 2 comma 1. So 2 in this direction, 1 in that direction. So right there.
2 comma 2.
Oh, I'm not counting very well, am I?
No.
Why? Why? So hard to count. So we plug in 1/2 comma 1. Let's do this. Let's do this first. Let's make sure that we have it written down. So 2. Do we agree it's going to be 2 comma 1? Yeah. Or with the vector notation. We all agree on that, right? It's just a question of counting to 2. That's the hard part. So 2 each. That's way over here.
2.5.
Oh.
So it's 2.
Yeah. That's the hard part. Okay, so 2 in the x direction, that brings us over to here, 1 in the y direction, so that should be in there. Does that look better? Yeah?
Yes.
Okay, good. The important thing is that it's perpendicular. It's got to be orthogonal to that level curve. And we use the ordered pair to build the corresponding vector. All right. Yeah, this first section is kind of terminology, nothing too difficult. We'll get into the nuts and bolts in the next section. So gradient field here for arctan. So gradient field, we use our triangle, our upside down triangle, our del. So del F, 2-dimensional vector field. We get 1 over 1 plus the inside squared times the derivative of the inside with respect to x in this case. Partial derivative of this with respect to x. Low d high is 0, minus high is d low over low squared. So like that. And then the second component, the denominator is the same, 1 over the inside squared. Derivative of the inside with respect to y is just 1 over x. Simplify this a little bit, and this will be our vector field, which is also a gradient vector field. So there's our gradient vector field.
How'd you get the x on top?
Multiplying top and bottom by x squared over here
Oh, okay. I see.
to clear that denominator. So multiply through by x squared.
I actually did that with the other one too. Right?
So nothing new really, except that we're going to call this guy the potential function. That's the only really new thing. Instead of calling it, we used to call it f, now we call it phi. Greek f. Greek f. All right, I'm done with that section.
Wait, what?
Now to the nuts and the bolts. Stamina.
Is this short? Or the homework?
All right.
When is this short?
Yeah, that's actually the homework you're gonna love.
There's 6 problems.
There's 6 easy problems. All right, let's get to the hard stuff.
I'm gonna really have to think about those ones. I don't know.
Gonna need a ruler. All right, so here we go. Here's the real stuff. This is what we've been waiting for. So line integration. This is our first adventure into integrating on an object other than the x-axis or the xy plane. We are now going to integrate on a curve. So they call it a line integral, which is kind of a misnomer. It's really a curve integral. So as you're moving along the curve, there is a function that assigns a real number to every point on the curve. And the integral is going to collect all those real numbers and add them together, finding area, essentially. So the easiest way to visualize a line integral is that you're finding the area between this curve in three-dimensional space and this curve down in the xy plane. So typically you imagine the curve in the xy plane, and the function is giving you a height all along that curve, so it's kind of like a curtain, and you're finding the area of that curtain. That's how you think of a line integral. So instead of your function just defined on the x-axis, it's now defined on a curve, soon to be defined on a surface. And so the line integral can be set up with a Riemann sum, same as it always is. We have a test value. We subdivide into all these little subintervals. We pick a test value in each subinterval. We have a function value, so that's representing the height, and then we have the length of each subinterval. Multiply that together, it gives you a little rectangular area. You add all those up, and you get the area of the curtain. And then as you let those subintervals shrink, you get a better and better approximation. When you take the limit, you get the exact area beneath the curtain, or area of the curtain.
And so pretty much the line in the xy plane, you call that's level curve, right?
It's who?
Huh?
It's what?
Is that called level curve or?
Oh, no, it's just a curve.
All right.
No, it's not coming from a surface.
All right. So, but the curve in the xy plane is pretty much the same as the curve up there, just without the z component. Is z set to 0?
Yes, that's right.
Okay.
Yeah, so you can think of the ordered triples in this red curve as having the same ordered pair, but then a z component, which represents the height.
Yeah, so we can't do stuff like this and then have it integrate over here.
Right. Yeah. The way we conceptualize a line integral is that for each point on the curve, there's a real number associated with it, which visually is easiest if you think of that real number as height. Obviously, if the numbers are negative, it gets, then you have signed area again, where you have some points above the xy plane and some below. But in general, that's kind of the easiest way to think about a line integral, is that you're adding up a bunch of function values that are defined on a curve or a surface.
Right. Yeah, well, we get to do stuff where we have the skewed height thing.
Skewed height.
Skewed.
We will do all sorts of things. Maybe that. Skewed height. I'm not sure exactly what we mean by skewed height, other than, I don't want to say it.
All
right, so
Going to a nation of people with average low height and then thinking that you're tall, that's skewed height.
Skewed height.
Yeah.
We're not going to do that. All right, so typically we're going to write our line integrals as integral of f ds. So why is there an s differential instead of an x or a y? Well, we've noticed in the past that whenever we're moving along a curve, that's what ds represents. ds represents a tiny change along a curve. Right? dx means a tiny change in the x direction, dy a tiny change in the y direction. ds means a tiny change along a curve, so we have to use a ds. Now that means integrating is a pain in the butt, because the only way this integration is going to fly is if this function is written as a function of s. So that would mean we'd have to do an arc length parameterization of the curve, then we could do it. There is a way around. Be assured. There is a way around. Okay, so this slide looks a little intense. Let's go through it carefully. This is old news right here. That is how we defined arc length as a function originally. We said that S, as a function of t, is the integral from some starting point, call it a, you can start at 0, whatever, doesn't really matter. But the upper limit has to be t. This creates a function of t, and if we integrate speed, we're going to get arc length. That's what that says. Integrate speed over time, we're going to get arc length. That's what that says. Now, you know in Calc 1, I don't know if what's the first fundamental theorem of calculus or the second. It's one of those things from the fundamental theorem of calculus where you take the derivative of an integral and you get the integrand. So if we take the derivative of both sides here, so if we say, hey, let's take the derivative with respect to t, and the fundamental theorem of calculus says you get the integrand evaluated at the upper limit. So that's fundamental theorem of calculus. Multiply both sides by dt, and you have this equation right here. You have that ds. So that is the super important part. This is going to be our evaluation method. Anytime we see a ds in a line integral, we can replace it with speed times dt. Speed times dt. Speed times time. Rate times time equals distance. Okay, so what this is showing us is that if we have a line integral, we're integrating a function along a curve, we can use the parametrization of the curve in general. We do not need an arc length parametrization. We can use any parametrization. We turn f into a bunch of t's. Right, so there's f. We have to, whatever we parameterize our curve as, then we take those coordinates, plug them into the function, multiply by speed times dt, and we can integrate it. All right, so let's do a couple. So, wait, I thought I had one at the bottom here. Oh, not yet. Did I skip a slide?
No.
Okay. All right, so this is just more of the same. This says if we're in 3 dimensions, the same thing holds. So if our curve is defined in 2-dimensional space or 3-dimensional space, same thing. We're going to take our ds and turn it into speed times dt. And if we're in 2 dimensions, we're just going to have a 2-dimensional sum of squares. If we're in 3 dimensions, we're going to have a 3-dimensional sum of squares. So no difference. If we're in 4 dimensions, we'd have the square root of square, 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 add together. No biggie. All right, so here we go. Now, notice first here that this one is going to be on the simpler side because they gave us an arc length parametrization. They gave us a parametrization according to arc length by putting an s instead of a t. We should probably confirm that. Let's confirm that it's an arc length parametrization just to be absolutely certain. How do we decide whether a parametrization is according to arc length? What do we do?
Take its derivative.
Take its derivative. And what has to be true about a parametrization that is arc length parametrization? What's this? Speed is 1. It's a unit speed curve is what we say.
Oh,
So let's see if it's a unit speed curve. So we take the derivative. The derivative is a vector. And that's going to be 1 over root 2, comma, minus 1 over root 2. And then we find the magnitude of that vector. And regardless of whether you use an s or a t, if the magnitude is 1, then it is parameterized according to arc length. It is a unit speed curve because the speed is identically 1, no matter where you are in the curve. Okay, so that makes it a little bit easier. So we can evaluate this. This parameterization is from 0 to 4. So we integrate 0 to 4. We replace all the x's in this integrand with s over root 2. Replace all the y's with 1 minus s over root 2. Combine them. So let's see. So we get s squared over 2 multiplied by y. So multiplied by 1 minus s divided by square root of 2, and that's ds. So this one's easy because we don't have to replace the ds with speed dt. So not too bad here. So then we just distribute and integrate. And try not to confuse your s's with other letters or numbers. S cubed divided by root 2 ds.
Why did they choose to make S
Should it be 2
Oh,
root 2?
prominent letter in this?
2 root 2, thank you. Yeah, great question. I think people used to write their s's differently. Back when everybody knew how to use calligraphy, right? Calligraphically. All right, so whatever we get with this, 4 cubed is 64 divided by 6 minus 4, well, one of those 4s is going to go away there. 2 root 2, so we really only have 3 4s, which is 64 again. So however we want to simplify this, etc. You get the idea. So parameterize the curve. So right now, what this is doing, this function x squared y is defined on this curve. If you want to know what that curve looks like, you would have to turn it into an xy equation. X equals this, y equals this, do a simultaneous mumbo-jumbo thing, get a curve, y equals some function of x. And that's the curve. And this function says, for every point on the curve, square the x, multiply by y, add them all up, and that's what you get. That's what it's doing.
Comes out to negative 48 times the square root of 2 plus 32 all over 3.
Did you say that?
Yeah.
Bueno. All right. Well, let's up the ante a little bit. Let's suppose we're not given a parameterization according to arc length. Let's suppose we have something a little more general. So first it says find a parametric description of the curve if it's not given. So here we have a line segment. We're masters at this. So the natural parameterization of a line segment is to take the velocity vector, which is really just the terminal point minus the initial point, multiply that by t, and add the initial vector. That's the natural parameterization for a line segment. And when you use the natural parameterization, t is always between 0 and 1. So there's parameterization for our curve, which is just a line segment in this case.
Should we parameterize it to S instead of T, or?
Nope. If you want to, you can. Doesn't matter. So what we're going to see is that it doesn't matter anymore if we use the theorem. So if we use you could, and then you don't have to change the ds. But if we don't parameterize it according to arc length, then all we have to do is this. So we're going to go from 0 to 1. Right, that's what we parameterized our line segment on the interval 0 to 1. You could have it 0 to root 2, 0 to 20. However you parameterized your line segment here. If you wanted to do it according to arc length, whatever this would be 0, and then this would turn out to be whatever the arc length is, or whatever the distance between those 2 points is. So 5 root 2 or something. So now x squared becomes 25t squared. Y squared becomes 25t squared. And now here's the part that we have to remember. So times r prime's magnitude, so speed. So let's put absolute value bars, and we'll put the vector in here. So that's r prime. Right? R prime is right there. R prime multiplied by dt. So that takes care of the non-unit speed curve thing. We just have to put the magnitude of the derivative there, which is speed. Now we're good to go. We know that that's going to be, that part right there is all equal to, that's going to be square root of 50, which is 5 root 2 down there. So we're going to distribute that into here. Or I guess we could pull it all the way to, let's pull it all the way to the front. So we're going to have 25 factored out. We're going to have 5 root 2 factored out. 25 times 5 is 125. So we have 125 root 2 out in front. And what does this turn into? Did I factor properly?
Maybe not.
Well,
I feel like I didn't factor properly.
Is that when
Well, if
you
you added them
add
together,
those
you get
two, then you get 50?
Yeah, then we get 50.
And then you have 50 times 5 times.
Yeah, so how come that didn't work? If I factor out the 25, oh, because then there'd be another 2 to factor out later. Because when we add the t squared plus t squared, we get 2t squared, and then we want to pull the 2 out to the front. So we will get 250 when all is said and done. We'll get 250 when we factor it all out. We're going to get 250 integral of t squared dt, 0 to 1. Okay, integrate that, we get t cubed over 3. T cubed divided by 3, 0 to 1. So we end up with 250 square root of 2 divided by 3. That is our final answer. Okay, so that function defined on that segment, we just added up all the z values or all the heights or whatever, however you want to think about it. It's like a skewed height problem, I guess. If you imagine your x comma y, x squared plus y squared is kind of like the, yeah, let's not try to visualize that. Okay, you're into skewed height. Try to visualize it. All right, so another one, parameterizing a curve. Now this is different. We've parameterized a million segments. Okay, a million minus epsilon. We've parameterized a lot of segments, but we haven't parameterized a lot of functions. But parameterizing a function is the easiest of them all. Can't we just do this if we want to parameterize a function? Can't we just let x be t? Right? We have an x and a y. If we have a function and we want to parameterize it, we just let the x component be t. And then plug in t there and we get t squared. Parameterizing a function is as simple as it gets because it's already a function. So if we let x be t, then y is just f of t. It's whatever the function is. So in general, like if we had something like this, y equals f of x, if we wanted to parameterize it, we would just say, just do that. If it's written to you as a function. Now, if it's not a function, if it's a curve, then we have to do a little bit more work if it's a relation and not a function. But if it's a function, simple as it gets. Okay, so now we have our curve parameterized according to t on an interval 0 to t, 0 to 1. So let's go ahead and evaluate this. So our line integral becomes the integral from 0 to 1 because that's our domain. And now the x in here gets replaced with a t. The y in here gets replaced with t squared. That's all raised to the 3rd power. Now here, it goes in there. Next is r prime's length, the magnitude of r prime, or also known as the speed. So let's come over here to the side. R prime is 1, 2t. And the magnitude of r prime is the square root of 4t squared plus 1. So that's what goes right here. dt. Everyone agree on that speed? Square root sum of squares? Right? Square root sum of squares? So now we do some math.
Okay.
Shocker. All right, we'll do some math. So this is t cubed to the, now it's just going to be t cubed to the 1/3, so it's just t. T times t squared is t cubed to the 1/3 is t to the 3 times 1/3, which is 1. Question?
Forgot your one.
I did?
Isn't
Oh,
it 4t
those are
squared?
Oh, that one. I thought you meant the one on the t up here.
Oh.
Wow, that
This
took
one.
me a s-
That
hot
one?
second.
That t, that one. All right, all right. Let's integrate. Derivative of in here is 8t, so let's force that to be an 8 and put a 1/8 out in front. So now we have u to the 1/2 du. So we should be able to do integration with substitution on the fly. So now we're going to get u. Our u is 4t squared plus 1, u to the 3/2 multiplied by 2/3, 0 to 1. And that gives us 1 divided by 12, 5 to the 3/2. We've seen that before. 5 to the 3/2 minus 1. So we get 5 root 5 minus 1 over 12. Imagine that. Imagine. Oh, that's right. All right, there. Okay. Go for it. You're up. Tag.
Tag.
You're it.
Oh, but this has three.
It's got 3 coordinates.
We're all gonna
Oh, do I
die.
really have to add 3 squares all together at the same time? Yep. All right, line segment. Let me know if you're having trouble parametrizing. First step is any of these line integrals, or when we get to surfaces, surface integrals, the first step is always parametrizing the object that you're about to integrate on, whether it's a curve or a surface. Let me know if you're having any parametrizing issues. Let's parametrize your issues. Parametrize the issue. Yeah. So this one is going to be very similar to that one where did we parameterize that line segment? Oh, is it right there? Oh, yeah, right there, sorry.
If you do like that normal.
So parameterizing a line segment.
Why is that? Oh, okay.
So the only difference is that we have 3 coordinates, so.
Okay.
Minus three.
Cool.
I did this minus that.
Right, so is that your initial point?
I'm probably wrong.
Can I confirm that? So if I do this minus this,
Mm-hmm.
so I get 2 to 2, right?
Mm-hmm.
Is that my initial point?
Yep.
This one is my
Yep.
initial point?
Yep.
This one.
Does it make sense? This is when you So you could go from here to here, or you could go from here to here. You could go either direction. That's the natural way to go, is use that as your starting point. But you can absolutely do that.
Is that wrong?
No, no. You just have to double check on your t, though. So when you parameterize in the opposite direction, we have to just check and make sure. So when you plug in t equals 0, you're at that point. When you plug in t equals 1, are you at the correct point there? No. So if you do the subtraction this minus this, then you're starting here. If you do the subtraction this minus this, then you're starting there. So for you, if you want to start at that one, then you're going to have -2, -2, -2 is this guy. Or you could parameterize from -1 to 0 too. You could let your t's go -1 to 0, or that would work also. So there's lots of ways you can parameterize. It looks pretty good. Square, add. All right, let's go through this. So there are literally unlimited parameterizations of a line segment. You can fiddle with your domain. You can fiddle with your starting point. You know, lots of different ways you can go. The natural way is typically to take the first point as your starting point, take the second point as your terminal point, and so you subtract terminal minus start to get the direction vector. All right, so let's parameterize it that way, but you could certainly do it in lots of other ways. So we're going to do 2, 2, 2 times t plus start vector, and t is going to go 0 to 1 if we do it this way.
How do you know that?
From the first chapter we did was all about parameterizing line segments.
No, the 0 to 1 part.
That's
From
back in that first chapter. Remember, if you plug in 0, you're at 141. And if you plug in 1, you add those numbers together and you get 363. So it's by construction. If you're going from here to here, then it's one, you can take one step to get there to there, then that's 0 to 1. If you parameterize it using little steps so the t goes 0 to 4, that would be different. So, like, for example, this direction vector points in the right direction, correct? It's pointing from this point to that point. What if we did this? Another parameterization would be 1, 1, 1 times t plus the same starting point. But here, we're taking smaller steps. What would the t's have to go between?
0 to 2.
0 to 2, right? Exactly. So if we divided that by 2, then we've got to extend our time. If we're going to take smaller steps, we need to take more of them. So we have to extend our t interval. And so it's not going to matter which one you use. Your t interval could be -1 to 0 also, depending on how you do your subtraction. Lots of choices. Lots of choices. So our integral, let's use the top one. We'll integrate 0 to 1. And then x, so the x, y's, and z's, those come from your parameterization. So those are, and I didn't combine these, but let's combine them into one vector. So this is 2t plus 1, comma 2t plus 4, comma 2t plus 1. So that is now x, y, and z. So when we go to the integrand, ooh, it's almost time for break. So when do we get cancellation?
Because x and z are the same.
X and z are, oh great, good observation. So we get 2t plus 4. 2t plus 4 multiplied by the speed. So the speed is right here. That's the magnitude of the parameterization. So the square root of 4 plus 4 plus 4, square root of 12, 2 root 3, times dt. 2 root 3 comes to the front. We integrate this, we get t squared plus 4t, 0 to 1, and we get 10 root 3. That would be our value.
That problem wasn't too bad.
All right, ready for a break?
Yes.
Okay, we'll take a break. Let's take a break.